there's some connection issues there.
Okay.
But anyway, that's I'll leave that to you.
I will just do this. Now we are.
There's some connection issues there.
Yeah. Okay.
But anyway, that's I'll leave that to you.
I will just do this. No.
That's right. Hearing myself back is slightly disconcerting, but usually that will go away.
So now we are online, and we are very excited about today's talk by Tim Cannings. He will talk about random projection ensembles from classification and dimension reduction. Thank you very much for agreeing to give this seminar, and the floor is yours.
Fantastic. Thanks very much. Yeah, for those in the Zoom call, I've actually got it set up. I've done a fair amount of online teaching now, where if you turn your cameras on, I will be able to see you. It's up to you, but if you turn cameras on, I can see. Fantastic. Yeah, as I understand, this is supposed to be a somewhat interactive seminar, so please do interrupt me and ask questions if you have them as I'm going through things. I guess one more thing before I begin. So yeah, I'm a lecturer at the School of Maths in Edinburgh, and I really do statistics. So if you ask me lots of difficult probability questions, I'm probably not going to know the answers. But let's see. And bearing that in mind, I'll sort of give a bit more of a gentle introduction to the problems I'm thinking about than maybe I usually would. If you're sort of all finding it very boring and you actually know these things, then please tell me and I can sort of speed up. But yeah, that's the plan. So this is actually work I did a fair amount of time ago during my PhD in Cambridge, and that's really the classification part of it. There's this little extra bit on dimension reduction, and if I have time, I'll say a bit about that. It's very much still work in progress, so we'll see how that goes. Yeah, and finally, thank you very much for the invitation. And yeah, as I said, it's great that you've come across my work and that you're interested in it. Okay, so yeah, this is joint work, or mainly based on joint work with Richard Samworth, who's a professor in Cambridge, and I did my PhD with him, and I've worked with him on many projects. And this was really our first project together, and it's a nice one, I think. So yeah, we're interested in classification problems, and this is sort of at least to begin with, is the sort of vanilla version of a classification problem. And what I get is that I get some data. These are my pairs x1, y1 up to xn, yn, and xi is like a feature vector in p dimensions, so just in r to the p here. This is a set of covariates for patients, for instance. And what I'm interested in is classifying things to either class 0 or class 1. For my existing data, I have the class data available. So this is sort of what people call a supervised classification problem. Okay, so I also get these yi's, and that tells me whether the observation came from class 0 or class 1. Okay, and we have this very simple task. We want to just predict the class y of a new observation x. So I get another patient that has its own set of covariates, and I want to maybe say whether it came from class 1 or class 0. And these classes, in this case, could, for instance, be patients who have a particular disease or not. And that's sort of what's depicted in this picture here. So these are actually brain scans. So this is sort of going beyond just having sort of simple covariates. And I really have a brain scan for each patient. And for a subset of the patients, they are healthy, and that's sort of represented by this picture on the left. So maybe we give those ones class, say they're in class 0. And then this plot on the right, or this picture on the right, looks somewhat different. You've got sort of more darker areas here, maybe, and some yellow areas here. And actually, this is a patient which is showing the early signs of Alzheimer's. Okay, and what we might think of doing is, well, we have a set of patients, some of which have Alzheimer's, some of which don't. And then we take a brain scan for a new patient, and we want to classify them or say whether they may be susceptible to Alzheimer's in the future or not. Okay, so this is sort of what I'm saying by the medical diagnosis application here. but this is a really broad problem, and it has applications in fraud detection, marketing, and spam filtering, and other things like that. So, yeah, this is sort of what your email spam filter does, is exactly this kind of thing, where it learns from your previous emails, that's the previous data, what is spam and what's a genuine email, and based on that it decides, when a new email comes in, it decides whether to put it in the spam folder or send it into your inbox. Okay, maybe I can ask at this point, just for the people in the room, have you heard of classification problems before? And I guess I should say before Lorena's presentation on this, or are you completely new to this problem? I guess this isn't something you'd come across as a probabilist. So maybe if people can raise hands or something, if you raise your hand if you have heard of classification problems previous to Lorena's introduction. Okay, I've got a thumbs up from one person. Okay, so it seems like not many people, at least not everyone has suddenly raised their hand, so not many people have heard of this problem. Okay, I hope it's clear. So this is very much the simplest form of this problem you could think about. Okay, and this is not a new problem. It's been around for a long time, and actually work on this dates back to sort of the 1940s, where Fisher developed this method called linear discriminant analysis. So that's sort of one of the really popular methods, is linear discriminant analysis, and that's sort of short to LDA, and that's what I'm depicting here. So yeah, let me say a little bit about LDA first. So here I've got two classes. I've got a red class and a black class. And I've got my feature vectors here are just some components. I haven't given them a meaning here, so I've got a first component and a second component. So my x values are sort of the specific, so this point here, if you like, this is this x1 is close to 1, and its x2 is close to minus a half or something like that. Right? So I've got a two-dimensional features here. And then the label is the color of the point. And the way LDA works is that it fits a model which says, well, I think that the red class is a Gaussian class centered somewhere with a certain covariance matrix, and the black class is another Gaussian centered somewhere else with the same covariance matrix. Okay, and then I find the maximum likelihood estimators for these parameters, and I then can think about this hyperplane, which is this sort of diagonal line here, which is hopefully separating the classes. Right? And yeah, what I do is I sort of end up with a line that goes between the class means, that's the sample means, this diagonal line going the other way, and at some point I need to separate along that line. Okay, so this blue point here is the one I want to classify, and we see that that's to the bottom right of the hyperplane here, so I'm going to classify that as being in the black class. Okay, that's just one method, and it's sort of the first method that was really studied in detail. There are many, many others, and just a few here: k-nearest neighbors, support vector machines, classification trees, and then things like random forests, and then more widely known perhaps, machine learning black box kind of methods. And this could go on for many, many pages of slides, but yeah, I'll stop there. Just to highlight how k-nearest neighbors works is that, again, so the data and the point I want to classify are exactly the same here. The way this one works, so I still want to classify this blue point. I look at the nearest neighbors of the point I'm interested in Euclidean distance in this case. And here I've got 1, 2, 3, 4, 5, 6 neighbors. And then I take a majority vote over the classes of those neighbors. So this time they're all from the black class. So again, I would classify this point to the black class. And I guess one difference between LDA and K and N is that in LDA, it'll always end up with this linear hyperplane. In K and N, it actually could be a very complicated decision boundary. Okay, so there are tons of methods. Why am I bothering to come up with a new one? In sort of modern applications, and many modern applications, including the Alzheimer's diagnosis, where I had brain scans. In those brain scans, I actually had a two-dimensional picture, but it's really a three-dimensional scan that you get. and it might even be changing over time. And you very quickly end up with a huge number of covariates, right? So in the plots here, I have just 2 covariates, but in many, many applications, I'm going to have hundreds, if not thousands of covariates. And if I think about images, I get something like, quite often like, high resolution images, and these have tons of pixels or voxels if I'm in 3 dimensions. And the issue is that many of these methods, many existing methods, sort of tend to break down in that setting. And there are lots of examples of how they break down or why they break down. But one that I could highlight here is that linear discriminant analysis is actually not even applicable if I have more features than I have observations. Right? And this is something that comes up a lot in modern statistics. Where I do have high-dimensional data, or I actually have more features than I do observations. And the reason is that this requires inverting a sample covariance matrix, and this is going to be singular if I have, it will be of rank n when I've got, it's actually a p-dimensional matrix of rank n, and if p is less than n, then it's going to be a singular matrix. Okay, so there's various methods to combat this, and one of the key approaches, which I won't really go into any detail about here, is to think about having sparse decision boundaries. Right? That's what I mean by this is that instead of thinking that all p of my features are important, I'm actually only there's only maybe a handful of them that are really important, and as long as I could somehow find those or find lots of them, or most of them, sorry, then I still should be able to come up with a good method. And various approaches to this include sort of penalizing a likelihood in the same way that something like the lasso works. Okay, but I don't want to say too much about those alternatives today. So instead we're going to use random projections, and I think, random projections are very neat because they're sort of very widely applicable. Right? I can always project my data into a low-dimensional space. I don't need to worry about coming up with a good model or anything like this. I can just project and sort of, let's say at this point, hope for the best, but we'll sort of say why projections are a useful tool throughout the talk. So when you first read about random projections, if you sort of Google random projections in statistics or something like that, you're bound to come across this thing called the Johnson-Lindenstrass lemma. And this is really the motivation for a lot of work on using random projections in statistics. And it has this very simple statement, at least slightly abbreviated here, where if you give me n observations in p dimensions, I can actually project them into order log n dimensions, and do this in such a way that I preserve all the pairwise distances. And actually, what I can do, so the proof of this result, which has nothing really to do with random projections, it's just a dimension reduction result. But the proof is based on random projections, where I say, well, I randomly project, and with positive probability, I find something that satisfies this criteria that I preserve all the pairwise distances. And if I have positive probability of something, then at least one version of this must exist. So that's how it works. And actually, sort of an extension to the result, which I guess is really the one used in statistics, is that I can do this in such a way, if I choose my lower dimension d in such a way, I can actually get this happening with high probability. Right? So it's not just that one exists, it's really with high probability after a random projection, I preserve the distances between the points. So if you think about something that is only based on the distances, like the k-nearest neighbor classifier, then what we can do in this case is start with our very high-dimensional problem, project it into our low-dimensional space with a random projection, which is just randomly chosen with IID Gaussian entries, in fact. And other things are possible there, but one option is to just have IID Gaussian entries. And then apply the method in the lower dimensional space, and I'm approximately going to get the same results that I would have done in the original space. And what this means is that we can massively reduce the computational time by employing this sort of random projection technique where I project and then my algorithm runs much, much faster in the lower dimensional space. So the projection is cheap, and hopefully my algorithm is not too bad in low dimensions. And yeah, this is going to work well when our original dimension p is very, very large. And indeed it does, and there are many examples of this being used. Okay, our motivation is maybe slightly different. So the Johnson-Lindenstrasse lemma says we can improve the computational time, but statistically we're sort of going to get very similar results. Right? It's preserving the distances. We can't hope to improve anything there. We're just getting similar results in faster time. Whereas what we want to do is really try and improve the statistical properties, let's say, of our classifiers. So there's this very simple fact. If I have two p-dimensional distributions, so here I've got the conditional distribution of class 0 and the conditional distribution of class 1, of the features, that is. If these distributions are different in the p-dimensional space, then for any d, including d is 1 in fact, there must be a projection which preserves some difference between the distributions. Right? So if I project into d dimensions with this projection A, then there's at least one A where I get a difference between these two distributions here. And okay, this plot here is sort of illustrating this in some sense. So I've got two distributions. One is uniform on the circle, on the outer circle here, and the other is uniform on the disk. And what we see is that if we project into one dimension, actually in any direction in this case, the disk becomes a sort of semicircle shape, whereas the circle becomes a sort of U shape. Okay, so here I could think about finding the difference between these two distributions by projecting into the one-dimensional space. Maybe one more thing to say about this is that this has a very simple proof based on characteristic functions. So just almost by the definition of characteristic function for a p-dimensional distribution, you can think about projecting into lower dimensional spaces. And if the characteristic function is the same for every A, then this is just telling you that the original distributions are the same. Okay, so this is very nice. There's a big caveat, which is that there exists a projection which is good for us, but most of the projections are actually completely useless. And especially when I go to high-dimensional problems, let's say I think here I have p is 100, and I'm projecting into two-dimensional.
Sorry?
Yeah.
I have a question.
Sure.
When you say distributions, is distributions in probability?
Here, this is yes,
That
distribution. Probability distribution on. So I have a probability distribution on R to the p for the 0 class, and a probability distribution on R to the p for the x is 1 class.
If they are the same?
If after I apply a projection A, if I have the same distribution for every A, then I must have the same distribution to begin with. So what this means is that if I have a difference in the two classes in the original space, which is really what I expect as I'm trying to distinguish between them, then there must be at least one projection where there's a difference here.
Okay, thank you.
Thanks. Yes, okay, so this leads on nicely. So there's at least one projection where there's a difference, but there's lots of projections, and in fact most of the projections are useless for me. So here I go back to an example where I have a black class and a red class, and yeah, the original dimension here is 100, and I've randomly, in the top row, I've randomly projected my 100 features into two dimensions. And I've done this by generating just a p by, so 100 by 2 matrix with IID Gaussian entries. And what we see is that, and okay, you have to trust me here, in the 50-dimensional space, these two classes are actually quite well separated. Okay, and what happens is that after any random projection, or any single random projection, the classes pretty much overlap, right? And what I want to do is really distinguish between the black and the red distributions here, And if I ask you to do that in any one of the three plots, and on the top row, it would be it would be hard to come up with anything that's just doing better than a random guess, let's say. Maybe you could, in the second example, maybe there are a few more red points over here, but it's really not, it's not obvious that there's any difference between these two classes. That's what's happening in the top row. In the bottom row, what I do is something only slightly different. What I do is I try, I think, 50 projections like I did for the top left one. I try 50 of those, and then I choose the best one that in terms of some estimate of a test error using the linear discriminant analysis classifier. Okay, so I apply these 100 projections, then I apply the LDA classifier. I sort of have some measure of its performance, in this case, I guess the training error, and then I keep the one that did best out of the 100 that I chose. Okay, and now in this case, you can see that there is some separation between the classes, and it's kind of clear that there's a lot more red points in the bottom left here, and perhaps if I wanted to fit a classifier, maybe I'd put a linear classifier, maybe I'd put a linear boundary somewhere around here, and that would quite well separate the black class and the red class. Much better than I could have done, certainly much better than I could have done for any random projection here. These other two plots are very similar, except that in the middle I'm using another method called quadratic discriminant analysis, which is very similar to linear discriminant analysis, but allows the covariance matrices to be different. And on the right-hand side, this is for the k-nearest neighbor classifier. And actually, it just so happens that in this example, I in fact got the same projection that I did for the LDA classifier. So these two plots are actually exactly the same. That wouldn't always happen, it's just a coincidence in this case. Not a complete coincidence, but basically a coincidence in this case. Now, doing this with any one projection, so for instance, if I pick this one here, it's clear that I've got this risk of overfitting, right? I've sort of chosen my projection because it was good for the data, and the way that we're going to get around this is then to fit repeat this process many times, a large number of times, and then aggregate the results in some way. And that's exactly what the random projection ensemble classifier does. So you can see this as a sort of add-on to any method that you like. So you choose your favorite classification method, and okay, in the end you might choose this based on the data in some way, or you might even sort of make some data-driven choice between the whatever options you have here. In all the examples I give, I either use LDA, QDA, or KNN. I'll say a bit more about those as I go. But here you could really use anything. Your only constraint is really the computational cost. You're going to apply this classifier many, many times. It needs to be relatively cheap to compute. So you don't want to be using something like a neural network as your base classifier here, because you're going to try and use it many times. Okay, so you choose your favorite sort of cheap classifier, and then I project the training data and test data, so the point you want to classify, at random into a low-dimensional space. So this is my d-dimensional space, a large number of times. I divide the projections into many groups of equal size, and then I choose the best projection in each group. And I do this in a way that I minimize some estimate of the error of my classifier. So in the top row here, these are just for random so for random projections, and the bottom row, this is after I've done one round of selection within one group. Then I apply this chosen projection, so I get one for each group. I apply the chosen projection and use the base classifier after applying that projection. Oh, that wasn't good. And then aggregate the results in some way. And what I do is actually use a data-driven biased majority vote. Okay, so there's two key things I've highlighted here. One is that we need to that we're going to choose a projection in some way, And the other is that I'm going to use a biased majority vote at the end. This is actually somehow crucial. Both of these are somehow crucial for this method being good in practice. So these are the two key messages. And I think this is really, the talk's aimed at doing classification, but I think this is really sort of true of if you want to employ some random projection methods in sort of, if your favorite statistical problem, let's say, then there's two key messages to take home here. One is that aggregating the results of applying all projections with sort of equal weights, if you like, is typically not going to be a good idea. Some projections will be good, some will just be noise, and you want to somehow filter out a lot of the noise here. And the way we're doing that is just to select the best one in each block. And the second thing is that you need a careful aggregation procedure. One thing that you might think about doing is just saying, oh, well, I'll just take a majority vote. If more than half of my projections say that I should classify the point as class 1, then I should say it's class 1. But actually we see, and I have some plots about this later, that in this problem, and I think in many problems, you really need to think carefully about how you aggregate the results of applying the projections. Okay, so yeah, that's I guess a sort of slightly high-level overview of the method, but it's all there if yeah, I have sort of presented the whole method in a way. There's there's quite a lot of things we need to decide on in terms of the distribution of the projections, and I guess related is the dimension I project into, which base method is the best to use. And yeah, in our paper that was published in 2017, we went through a lot of these questions in more detail. I don't have enough time to cover all of them. My plan for the, I guess, next 20 minutes or so was to at least present some of the theoretical results that we have. But maybe now is a good point to pause for 10 seconds, just in case anyone wants to ask anything.
Yeah, I have a small question. In the paper, you mentioned that B2 or I mean the projections you use in each of the chunks to select the one you're gonna use it has like a limit, an upper limit, no? So it can't be very large because you're gonna get noise or you're gonna overfit.
Right.
But
exactly.
you don't have that for the B1. I mean, for how many times you're gonna repeat the process of selecting the chunks and doing the projections and selecting one, and that's it. You don't have a limit for that, and I don't think so. But
Okay.
how well? I mean, how varying that how affects the algorithm?
Okay, so this is actually one of the questions I was going to answer in maybe about 4 slides time. So
Sorry.
it's a fantastic question, and hopefully I'll get on to, well, let me move on, and then you can ask again if I haven't answered it.
Yeah, sure.
Yeah, okay, so I want to do a bit of theory here, so I'm going to introduce a bit more notation. So yeah, remember that we get some data and we want to classify our observation X into either class 0 or class 1. And we do that with something that I'm just going to call a classifier. So this is just a function that takes a point X in R to the P, it takes a feature vector, and it needs to return either class 0 or class 1. Okay, and the interpretation is here that we're assigning the point X to the class C of X. Now, I can measure the performance using this thing called the risk, which is just the probability that I made a mistake. Right? So I've got some probability that C of X is not equal to Y, and this is what I call in the risk. And there's this nice fact that this is minimized by something called the Bayes classifier, and this is sort of coming from, I guess, sort of decision theory type arguments, where if your regression function eta is greater or equal to a half, then you should be assigned to class 1, and if not, you should be assigned to class 0. Okay, and eta here is just this regression function, so the property of y is 1 given x. Now, we don't know this function eta in practice, so we're going to use our data to somehow approximate it. Okay, so yeah, we want to talk about, we want to know how we choose the number of projections we're going to use. Is capital B1 here. So let's say that these, I just have projections that are independent random projections from R to the P to R to the D. Actually, I only need them to be conditionally independent given the training data. So here I can generate these projections based on the training data. And the way our sort of proposal works is exactly to do that. I generate lots of independent ones, and then I choose one in each block to minimize some test error. And the ones that I choose are these A1 up to AB1. So I end up with B1 of these in the end. And what I want to know is how does my classifier perform for different values of B1. Okay, so how does the method work? Very quickly, I project the data using each one of these projections, and then I train my classifier. Let's say it's LDA. I train my classifier using the projected data. That's what I get here, and then I just aggregate. I aggregate the results. I just take an average of the proportion of times. Just calculate the proportion of times that I assigned it to class 1. Okay, and then I do this biased majority vote. If the proportion is greater than alpha, then I assign you to class 1, otherwise I assign you to class 0. Okay, this is how the method is going to work in the end. Alpha will be chosen based on the data, and I'll come back to that very briefly, I think, towards the end of the talk. So this is, at the moment, just for some alpha in 0, 1. In particular, it's not equal to a half. This is a crucial thing. Okay, so what I could do is think about a sort of infinite simulation version of this, where instead of B1 projections, I actually get infinitely many projections. And the way that I can think about that is that I just think about the probability over my projections here that I assign my point to class 1. Okay, so if I go back one side, I had my sample proportion, if you like, is this mu n. And here I'm just taking its expectation to get a mu n. And then there's a slight typo here. This shouldn't have a hat. This should just be this mu n. If my mu n is greater than alpha, then I assign you to class 1, and otherwise you should be in class 0. There's another typo there. Okay, I've got slightly confused between zeros and 2s here, but hopefully wherever you see a 2, it should be a 0. Sorry about that. Okay, so I could say that these things are the distribution functions. The details here are not so important. What I'm interested in is this error, which I've now called the test error. It's very closely related to the risk. The difference here is that I'm only averaging over the test point. Okay, so I fixed my training data, and here this could be random because it depends on random training data, or it could be random because it depends on random projections. Okay, so hopefully this is the answer to your question. As I increase B1, the expected test error of my random projection ensemble classifier approaches the test error of this infinite simulation version at the rate of big O of 1 over B1. Right? So here, this sort of tells you how much. This tells you what the effect of getting more and more projections is going to have.
But just so you have that. I mean, more the bigger is B1, the better the simulation works, the algorithm works. But you have like it stabilizes, right? So in computational operations, how much it costs to how much you gain, or it doesn't seem so different to choose like B1 300 or 500
Sure,
in terms of
exactly.
performance.
So this is telling you, there's a little bit hidden here. We actually have sort of the leading order constant as well in this case. But essentially, yeah, this tells you that this is converging relatively fast. And you can see this in the plot even. So here, this is, the black line is the mean, and the red line is plus or minus 2 standard deviations. And actually, you know, after taking B1 as 100, you're getting already quite close to what you get on average towards the end, right? So here, yeah, I guess one way of looking at this is thinking, well, it is converging, it's converging quite fast, but I really want to take B1 as large as possible up to whatever computational constraint that I have. The other, you might say, well, actually, yeah, I know I don't have infinite computation, and I've already done 200 projections, and I've got to this point. Is it worth me doing any more? Probably not, unless you really care about these small fluctuations. Then it's not worth doing anymore. So, yeah, I think this is sort of it's really driven by the computational resources you have and how much you care about getting really super, or the best results you could get with this. Or maybe you're already happy with sort of an 11% error here, and then you might stop at, you might say, well, 200 projections is enough for me. Does that help answer your question?
Yeah.
Okay, great. Yeah, so that's what happens as B1 increases. Another result that we have actually holds for any B1. So, of course, in practice, you only use a finite number of projections. And it is nice, it would be nice to have some results about that. And this is exactly what this theorem tells us. Yeah, it might not look like it, but this is really just a fancy version of Markov's inequality. So you sort of apply Markov's inequality twice in different stages here, and somehow this result drops out. I think it's very nice. So this is essentially saying that, for any value of B1, however many projections you use, you can think about your average error here. This is going to be bounded by what happens if I just use one projection. Okay, and then I've got to rescale by this minimum of alpha and 1 minus alpha here. But this term here, this is the excess, like the excess risk, if you like, of just using one random projection. And that's actually something that we can then think to control, and really, I guess in some sense, serves as the motivation for how we chose the projections in our final algorithm. Okay, just to highlight that we don't need any assumptions here. So this is true for any configuration of training data, any distribution generating the data P, and any distribution of projections. This is really a very general result. Okay, so this serves as our motivation for sort of how we choose our projections, and what we want to do is sort of essentially try and minimize this right-hand side. So here's sort of the one of the inner loops, I guess, on how I choose the projections. So we generate a large number. There's B1 times B2 of them. And here I just say, according to Haar measure, actually this is not too important. And in many cases, I can replace Haar measure just by IID Gaussian entries. Okay, after each projection, I estimate the test error of the base classifier. And there are many options for this. It might be the training error, or it might be some leave one out error, it might be some cross-validation error. Again, I want something that's relatively cheap to compute. So out of these, the training error is by far the quickest. Okay, and then for each B1, so for each one of these blocks, if you like, I'm going to select a projection from the group, and then there's B2 projections in the group. And I'm going to choose the one that yields the smallest test error. And let me not say too much. The choice of B2, as Lorena mentioned, you sort of you don't want it to be too small because you want to be able to choose good projections, but you also don't want it to be too large because at some point you'll start to overfit. Right? If you use a very large number B2, then you're going to sort of lose some of the diversity, I guess, that you get in the ensemble. Okay, and then I use the selected projections in the generic version of the classifier that I already presented. Okay, I think one last thing before I show you a few simulations to try and convince you that this works. I need to choose my alpha, and I'm really not going into the details at all here, but there are two options. Well, okay, there's not one of these isn't really an option. How I would like to choose it is this oracle choice, right? And that's given by the black curves here, unfortunately I don't know the black curves. That's why I call it an oracle. It depends on the distribution, but I can sort of estimate this. It's not really a good estimate, as you can see, but I can somehow I have this red curve which is somehow related to the black curve. It's like a sample version, and then I can choose my alpha to minimize the red curve. And what we see is that we don't approximate the curve very well, but in many cases we do approximate the minimum quite well, especially when I get larger samples, which is this the bottom line here. Other thing to note here is that in many of these cases, so especially here, we're doing much better by using this data-driven choice of alpha, which is closer to 0.4, than using the sort of naive threshold of just a half. Okay, so I've got a large simulation comparison. I think I will relatively quickly go through this, but hopefully this will convince you that this method does actually do something interesting. I'm comparing with a whole load of different things, and I appreciate that these might not mean anything to many of you, but maybe you see your sort of favorite classification method here. If you don't have a favorite, maybe you at least see one that you have heard about. Okay, but there's lots of different methods. So what I'm going to do is generate some data, and I think this is all based on simulations. I do have some real data in the paper, but I don't think I have any of that in the talk. So I'm going to generate some data from a particular distribution, apply all these different methods and calculate the risk, and I'm going to estimate the risk over 100 repeats of the experiment. Okay, and maybe I should say here that all the standard errors, sort of Monte Carlo errors here, are less than 0.1, I think. So if you're sort of comparing numbers here, you want to think about one has to be sort of 0.1 better than another before it is really better. Okay, and I've got a subset of the classifiers in each case. So here I've got this sort of Gaussian example where the classes are Gaussian centered at different means, and they also have different covariances here. And I said at some point there's lots of methods based on sparsity. What I've done is introduce this rotation matrix to make sure this isn't a sparse model. If I have a sparse model, then the sparse models will work very well. This rotation R is sort of meaning this isn't a sparse model. But the way I've set this up with the parameters is that there's only a three-dimensional problem here. Right? The rest is sort of the other 97 dimensions are sort of like noise dimensions. Okay, and in this case, the Bayes risk, the best I could get is around 4%. Okay, and what we see here is that our method, which is this time with the LDA-based classifier, which is what the LDA stands for here, and I'm projecting into 5 dimensions. And if I remember correctly, this is always with, maybe I had it here, always with B1 is 500 and B2 is 50. Okay, so I have 50 projections in each block. I choose the best one and I aggregate over 500 projections in the end. So maybe 500 is slightly overkill here. Maybe I could have got very similar results with just 200 or something like we saw in the earlier plots. Okay, and here we see we do very well. Notice one thing is that the LDA classifier in this first case is actually not applicable. So I've got 50 dimensions and 50 observations and 100 dimensions. And this goes back to what I mentioned at the beginning, where this is, I get a singular covariance matrix here, so I actually can't apply this method in that case. But by employing the random projection techniques, we can apply the method, and actually we do very well here. if I have lots and lots of data, okay, well, maybe you wouldn't say this is lots and lots, but as I get more and more data, some of these other methods also start to do well. So this radial Gaussian process also does well in this example. Okay, that's the first thing. This next one I have is sort of like a mixture distribution for each class. Yeah, I'm sort of mixing between something that's sort of at plus and minus and something that's at these endpoints here. I think I'm actually supposed to be on the diagonal with this is basically designed to mean that random forest does very badly. So random forest is this very widely used method. In this kind of example, it actually can't deal with this at all, and you can see that here. Its error is close to just randomly guessing. Right? This is percentage error, so it's close to 50. And okay, with small samples, actually none of the methods do really very well here at all. And one of the best things is to just naively apply k-nearest neighbors in the original space. But as we get a bit more data, we actually start to do very well in this example, and basically nothing else except this another ensemble method. This time based on trees. This is called optimal tree ensembles. That one does start to do well, but again, we're still doing better. Okay, a very similar story in this case. Just to point out here, I used the QDA-based classifier as opposed to the LDA one, and again, I see this issue that the vanilla QDA method is just not applicable in these two settings. Again, because I need to invert a singular covariance matrix. Yeah, this final example, I use QDA and try KNN as well. And yeah, we see a similar story, let's say.
I have another question.
Sure. Go ahead.
So here we're seeing the error between the algorithm and the sample you have. But and you are choosing the parameters and mainly alpha to optimize this, minimize this error. But would there be like a way in choosing that threshold for alpha so you can control if you have a false negative? Because in some cases, I mean, it's not the same to get a false negative that a false positive. In some cases, like in sickness and diseases, it's worse to get a false negative, right? So would there be a way to choose this alpha to try to control this type of error, or it doesn't have?
Yes, I think, yeah, okay. I think I might wrap up and then come back to your question, because I think I'm close to, well, I have more slides, but I think it makes sense to sort of get to the end and then move back rather than jumping around. Okay, so I have a real data example, which I think I will skip. And I have a summary so far, but this is actually going to be the final summary, because I think I'm sort of running out of time. So yeah, random projections of this very general methodology, and we see that this is sort of a showcase for them in classification problems, but there are other problems in which we sort of think they might be useful. There's a lot more results in the paper, and I'm very happy to answer more questions after I answer this first one. Yeah, I had some slides about dimension reduction, which I'm just going to flash up and then skip to the end. So let me go back to this choosing alpha. Yeah, so here I've plotted two things. I've plotted this oracle choice and a practical choice. And yes, the oracle choice is really targeting minimizing this type of error, right? This test error, or if I go back to this type of error. And I guess this is sort of the simplest measure of performance in a classification problem, but there are many other options. And yeah, we have, you might have heard of things like ROC curves. So receiver operating characteristic curves. You might have heard of precision recall curves. And these are sort of relating these different types of errors that you get, right? I could wrongly diagnose someone who's healthy as a disease patient, and I could wrongly diagnose a disease patient as healthy. And you're exactly right that these sort of different errors have different trade-offs, or different sort of costs associated with them, right? It might be quite serious if I say someone who's actually very unwell is well, and if I say that someone who's healthy is unwell, maybe they only go for follow-up tests, and it's not such a problem. So yeah, something you might want to do, and there's a framework in classification called the Neyman Pearson framework, where I want to sort of limit my number of let's say false positives, or my chance of a false positive, to being less than some threshold. They typically use the value alpha, but I won't use that because I've got alpha meaning a different thing here. So they typically use this, say that, yeah, I want my false positives to be bounded by some threshold. Now, we could certainly try and do something like that here. One issue we have is that in that case, I think what we would need to do is actually be able to very closely estimate these black curves. So these are actually just a mixture of these two errors, and I could definitely decompose those and plot them separately, and then choose the threshold where one of them goes above whatever my desired level is.
Okay.
And that would work perfectly well. What I would need to do is estimate, I'd actually have to estimate this curve well, which, as you can see here, we're not really doing, right? We're really underestimating the errors. It's just that the minimum for us turns out to be in a good place. One way you can do this, and this is sort of widely used in this Neyman Pearson framework, is to have you hold out some data, or do something called sample splitting, and then I estimate what I want to estimate on the second half of the data, which has been held out from the first half, and then I would get a good estimate of this black curve, and then I'd be able to do something along those lines. The problem is that when I split my data, I essentially half the amount of data I have, right? So I lose a lot of statistical power. So you've got to be very careful when you apply these kind of methods. Yeah, in theory you get some very nice results, but in practice you sort of lose out quite a lot on statistical performance. Yes, but I think there's certainly a way you could do that, but it would require some sample splitting here. And yeah, maybe I could spin this around and say this is sort of another nice flexibility of this framework, where we can choose alpha in different ways depending on what measure of performance you want to minimize.
Okay, thanks.
Great, no problem. Yeah, okay, so it's 3 o'clock, maybe I'll stop there. I'm happy to answer more questions if people have them. Otherwise, thanks for listening.
Thank you, Tim. It was a really nice talk. Are there some other questions?
Yeah, I have a little question about page 15, I think.
Oh, okay. This one?
Yeah, thank
Okay.
you. When you say distribution of projections, you mean distribution of projected data or distribution of the matrix of the projection matrices?
The distribution of the projection matrices themselves. So here, here the data is actually fixed. So it's sort of a little bit hidden here. Maybe I fixed my training data. So the randomness I have in this term here, the randomness I have is randomness of the projections, and that's it. Otherwise, this is a deterministic value. And yeah, here it's over the distribution of the projections. This means that I could use any distribution of projections here, and this would still hold.
Thank you.
Okay.
Cesar or Carlos, you have a question?
Yes. Yes, I was wondering if it makes sense to compare these results with a non-supervised method like principal component analysis, which also works for like reduce to reduce the
yeah, so that actually ties in very nicely with some current work I'm doing on label noise. So for certain cases, in certain distributions, it actually makes sense to ignore the labels and do exactly as you say, do some clustering algorithm. And you might actually be able to do better by, actually, sorry, that's not true. I don't think you can do better. But you can do just as well by ignoring the labels that you have and applying some clustering method, like you say, like PCA, and then it separates the classes. Intuitively, that sort of doesn't make sense, right? You kind of think that if you have labels, you should use them. And I think that is still true. In some sense, you need to use them at some point. I guess, yeah, maybe I won't go back to the results, but if you might separate into two classes very well, but you still need to know what class corresponds to what in the end, right? You can't. If you do your clustering method, you get class A and class B, and you need to know how that relates to class 0 and class 1. Yeah, I'm sure in some cases these clustering methods would get sort of similar performances, but I expect that actually using the labels is you're going to do much better than not using them.
Okay, thank you.
Okay, thanks.
Uriel, do you have question, comments? No, doesn't seem to be the case. Yeah, Lorena?
Yeah, just one thing, little. Does this algorithm is available or implemented in R or Python libraries?
Yeah, there's an R package called RP Ensemble, yeah, it's on CRAN. So if you, I think if you go via if you can't find it on CRAN, if you go via my website, you should be able to find it.
Okay, cool, thanks.
Yeah.
That was it.
Okay, great.
Great.
Well, thank you very much, everyone, for getting up early and listening in.
Yes, thank you, Tim.
Yeah.
Well, I am still recording. Let me stop this.